Okay folks, in this video what we're going to look at are two work problems on related rates of change. Now the challenge for these is pretty much the same as the challenge you find in optimization. That is trying to get the relationship between the two things that you're trying to get the rates of change for. Now in this particular problem we have a balloon, we'll assume it's spherical, and we're blowing it up. So the radius, it says, is increasing at the rate of 0.75 centimetres per minute. What we want to do is find the rate of change of its volume when the radius is 5 centimetres. So as the balloon increases in size, the radius is increasing, and of course at the same time as the radius is increasing at its rate, which is 0.75 centimetres per minute, the volume will also be increasing, but it won't be increasing at 0.75. because there's not a direct relationship between those two variables. So what we have to work out is some sort of relationship between the rate of change of the radius and the rate of change of the volume. That's the goal. So generally speaking, similar to, hang on a second, just bring that back up. Similar to the optimization problem I talked about before, you'll nearly always in these sorts of problems be given some specific information, and that's usually where you start. Now in this case we've got two pieces of information provided. We've got the rate of change of its volume when the radius is 5, and the other thing we've got is that. Now it says the radius increases at a rate of. So that number is actually the value of the rate of change of radius with respect to time. See, centimetres per minute is a rate. So that's dr dt. So what they've told us is we've got a rate of increase of radius, which is constant at 0.75 centimetres per minute. And we want to know, and we've got this other value, which is 5, which is an instantaneous situation where the radius is 5 centimetres. We want to know what's happening to the volume. So we know that the volume of a sphere is 4/3 pi r cubed. Now, the information, so I can get the derivative of that. So dVdr is 4 pi r squared because it's just the power rule. If you grab the 3 up here, bring it down, multiply, that 3 cancels with it, so you get 4 pi r and the 3 reduces by 1 to 2, so 4 pi r squared, no big problem. Now, we know that the rate of change of radius is 0.75. So let's see how we can now use that. So dr dt therefore is 0.75, but what we want is the rate of change of volume. So we know the relationship between these things, and this is often these related rates of change. What you do is you use the chain rule. We know over here we've got dr dt. What we want to know, when we also know that the dV dt is dVdr dr dt. So there is dr dt there. So what I've now got is dr dt is a number, which is 0.75. That's the bit at the back. And dVdr we've just worked out up here, which is 4 pi r squared. So we can now substitute in that right-hand side for dVdr and dr dt in terms of the things we've worked out, and we have an expression for dV dt. So dV dt is 4 pi r squared, which is dVdr, times 0.75, which is dr dt, which came from the data in the problem. So the rate of change of V when, with respect to time when r is 5, I just take 5 and put it in there for r. And you'll end up with 4 pi times 5 squared times 0.75, which comes out to 75 pi centimetres cubed per minute. Notice that the unit here is, I've just put the units in there. R is squared, so the unit of R is centimetres, so that's centimetres squared. The rate of change of R is centimetres per minute, so we now have centimetres cubed on the numerator and minutes in the bottom. So that's the unit for it. So there's one problem. So as the rate of change of R is 0.75 centimetres per minute, the rate of change of volume is 75 pi centimetres cubed per minute. Second problem. Now this is a similar one to one we've had before. I've already solved it, but we'll do it again. In this problem we have a car travelling north towards an intersection at a rate of 60 kilometres per hour while a car is travelling east away from the intersection at a rate of 50. So you can see that if I consider the intersection, we've got a rate, one car has a rate travelling towards it, one car has a rate travelling away from it, but there is also a distance between the cars, and that will also be changing. So what in this situation we've got is 3 interrelated distances. They are all related to each other, but they are all changing at the same time. So what we need to do is have a look at how we can relate those changes together. Now we know what this one here is. We have 60 kilometres per hour. That's a rate, kilometres per hour. Now that's the rate at which a car is travelling towards the intersection, travelling north. 50 kilometres an hour is the second rate. That's the rate of the other car going east away from it. What the question is asking for is the rate of change of the distance between the cars and the car and the truck. So that's what we need to do. So we have a situation here where we'll set up the problem. We've got the car travelling north. That's the X car. The car travelling away from the intersection is the Y car. And the Z is the distance between the two cars. So X will be the distance from the north travelling car from the intersection. Y is the car travelling away. And each of these things will be changing with respect to time. So the rate of change of that one with respect to time is dx dt. That one is dy dt, and the distance between the cars is dz dt. Now, before I can get a relationship between the 3 rates of change, I want to come up with a relationship between the 3 values themselves, and that's fairly obviously from going to be Pythagoras' theorem. So what we've got so far are these two. dx dt is negative 60 kilometres per hour because x is getting smaller. Dy dt is 50, and that's just coming from the problem. We have x squared plus y squared is z squared, which is Pythagoras' theorem in terms of the distances. So if I just get the derivative of everything with respect to t, we get the ddt of the left is the ddt of the right. Now this is, we have to use the chain rule because the ddt of x squared is not just x. If it was just x, it would be dx dt. But it's not x, it's x squared. So to use the chain rule, it's the derivative of it with respect to x first, then the derivative of it with respect to t. The derivative of that with respect to x is 2x, dx dt. Derivative of that with respect to y, dy dt. Derivative of that with respect to z, dz dt. The 2's just cancel out because it's common to every element. Transposing everything, because remember, dz dt was the thing we're after. So taking everything over, we end up with dz dt is x dx dt plus y to y dt all over z. And if you substitute in to there, we will get all of the required values. We already know that that one and that one from the problem, they were the 50 and 60 kilometre an hour numbers. X and Y are these two numbers, 3 kilometres, X is 3, Y is 4. Z is the distance between them. Now, if that's 3 and that's 4, we know that that must be 5 by Pythagoras' theorem. It's a 3, 4, 5 triangle, and that will give us the Z. So every number on that right-hand side is provided. We substitute it all in, and we end up with that, and you get 4 kilometres per hour. So we won't worry about logs, so we'll go back. Okay, so there's another example of a related rates of change problem. Usually they work similarly to this. What you've got to get is identify the different variables that you're trying to relate together, like we did in the last one as well. Then you get the derivative of the two things, because that will give you both of those terms as derivatives. The challenge is often trying to get the derivative with respect to the right quantity. And every problem is very hard to give any direction on that because every problem tends to be different.